Learning objectives. In this chapter, the user would learn the following in detail: time domain analysis, frequency response graphical interpretation, application digital audio effects, signal processing techniques allow us not only to compensate for the acoustics of a listening environment, but also to add special musical effects such as delay, echo, and reverb if desired. The most common example is the audio equalizer that allows us to enhance the bass and treble content of an audio signal. In any listening space, what we hear from an audio source consists not only of the direct sound but also early echoes reflected directly from the walls and other structures, and a late sound or reverberation that describes multiple reflections that get added to other echoes. The amplitude of the echoes and reverberation decays exponentially with time. Together, these characteristics determine the psychoacoustic qualities we associate with any perceived sound. A conceptual model of a listening environment consists of echo filters and reverb filters. A single echo can be modeled by a feed-forward system of the form y of n equal to x of n plus alpha into x of n minus d, h of z equal to 1 plus alpha into z power d, h of n equal to delta of n minus alpha into delta of n minus d. This is just a comb filter in disguise. The zeros of this filter lie on a circle of radius r equal to alpha power 1 by d with angular orientations of omega equal to 2k plus 1 whole power 1 by 4 equal to d. Its comb-like magnitude spectrum h of f shows minima of 1 minus alpha at the frequencies f equal to 2k plus 1 divided by d and peaks of 1 plus alpha midway between the dips. A reverb filter that describes multiple reflections as a feedback structure of the form y of n equal to alpha into y of n minus d plus x of n, h of z equal to 1 divided by 1 minus alpha into z power minus d. This filter has an inverse comb structure and its pole lie on a circle of radius r equal to alpha power 1 by d with an angular separation of omega equal to 2 pi divided by d. The magnitude spectrum shows peaks of 1 by 1 minus alpha. At the pole, frequencies f equal to k equal to d and minima of 1 divided by 1 minus alpha midway between the peaks. Conceptually, the two systems just described can form the building blocks for simulating the acoustics of a listening space. Many reverb filters actually use a combination of reverb filters and all-pass filters. The reverb filters in above figure typically incorporate irregularly spaced delays to allow the blending of echoes, and the all-pass filter serves to create the effect of early echoes. The all-pass filter has the form h of z equal to minus alpha plus z power minus l divided by 1 minus alpha into z power l equal to minus 1 by alpha plus 1 by alpha minus alpha divided by 1 minus alpha into z power minus l. Gated reverb and reverse reverb. Two other types of audio effects can also be generated by reverb filters. A gated reverb results from the truncation, abrupt or gradual of the impulse response of a reverb filter, resulting in an FIR filter. A reverse reverb is essentially a folded version of the impulse response of a gated reverb filter. The impulse response increases with the time, leading to a sound that first gets louder and then dies out abruptly. Chore using, flanging, and phasing. The echo filter also serves as the basis for several other audio special effects. Two of these effects, chore using and phasing, are illustrated in below figure. Chore using mimics a chorus or group singing or playing in unison. In practical, of course, the voices or instruments are not in perfect synchronization nor identical in pitch. The chore using effect can be implemented by a weighted combination of echo filters, each with a time varying delay dn of the form y of n equal to x of n plus alpha into x of n minus dn. Typical delay time used in chore using are between 20 meters and 30 meters. If the delays are less than 10 meters but still variable, the resulting whooshing sound is known as flanging. Phase shifting or phasing also creates many interesting effects and may be achieved by passing the signal through a notch filter whose frequency can be tuned by the user. It is the sudden phase jumps at the notch frequency that are responsible for the phasing effect. The effects may also be enhanced by the addition of feedback. Plucked string filters. COM filters, reverb filters, and all pass filters have also been used to synthesize the sounds of plucked instruments such as the guitar. What we require is a filter that has a COM-like response with resonances at multiples of fundamental frequency of the note. We also require that the harmonics decay in time with higher frequencies decaying at a faster rate. A typical structure first described by Karplus and Strong is illustrated in the Karplus-Strong structure. The low-pass filter has the transfer function GLP of Z equal to 0.5 into 1 plus Z power minus 1 and contributes a 0.5 samples phase delay. The delay line contributes an additional D sample delay and the loop delay is thus D plus 0.5 samples. The overall transfer function of the first structure is H of Z equal to 1 divided by 1 minus A into Z power minus D into GLP of Z, where GLP of Z equal to 0.5 into 1 plus Z power minus 1. The frequency response of this Karplus-Strong filter is shown in for D equal to 8 and D equal to 16 and clearly reveals a resonant structure with sharp peaks. The low-pass filter GLP of Z is responsible for the decrease in the amplitude of the peaks and for making them broader as the frequency increases. If A is close to unity, the peaks occur at or very close to multiples of the fundamental digital frequency F0 equal to 1 equal to D plus 0.5. For a sampling rate S, the note frequency thus corresponds to F0 equal to S equal to D plus 0.5 into Hz. However, since D is an integer, we cannot achieve precise tuning control of the frequency. For example, to generate a 1600 Hz note at a sampling frequency of 14 kHz requires that D plus 0 is to 5 equal to 8 is to 75. The closest we can come is by picking D equal to 8 to give a frequency F0 equal to 14, 8 is to 5, 1 by 4, 1647 Hz. To generate the exact frequency requires an additional 0.25 sample phase delay. The delay of this all-pass filter at low frequencies at least is approximated by DAP approximately equal to 1 minus alpha divided by 1 plus alpha. Alpha approximately equal to 1 minus DAP divided by 1 plus DAP. In order to implement the 0.25 sample delay, we require alpha equal to 1 minus 0.25 divided by 1 plus 0.25 equal to 0.6. In order to synthesize the sound of a plucked instrument, we require a reverb or comb filter with its integer delay to provide the multiple resonances, a low pass filter to ensure that the resonances decay with frequency, and an all pass filter with its fractional delay and a constant gain to fine tune the note frequency. Frequency response graphical interpretation. Graphical representations of the frequency response. One of the reasons why frequency response is a powerful tool is that it is possible to succinctly understand its primary features by means of plotting functions or parameterized curves. In this section, we see how this is done. Some of this may seem a bit pointless at present. However, as matters develop and we get closer to design methodologies, the power of these graphical representations will become clear. The board plot. What one normally does with the frequency response is plot it. But one plots it in a very particular manner. First we write h underscore in polar form. H sigma of omega equal to modulus of h sigma of omega e power I at an angle of h sigma of omega, where modulus of h sigma of omega is the absolute value of the complex number h sigma of omega and angular h sigma of omega is the argument of complex number h sigma of omega. Together, these two plots comprise the board plot for the frequency response h sigma. The units of this plot of 20 log modulus of h sigma of omega are decibels. One might think we are losing information here by plotting the magnitude and phase for positive values of omega. Example, in all cases we have A equal to first row of the matrix 0, 1, and then second row minus k by m minus d by m. It is of the order 2 cross 2. Then B equal to first row 0 and second row 1 by m. It is of the order 2 cross 1. Solution. We take m equal to 1 and consider the various cases of d and k. Here we can also consider the case when d6 equal to 0, 1. We take d equal to 3 and k equal to 2. With c equal to 1, 0 and d equal to 0, 1, we compute h sigma of omega equal to 1 divided by minus omega square plus 3i omega plus 2. Next, with the c equal to 0, 1 and d equal to 0, 1, we compute h sigma of omega equal to I omega divided by minus omega square plus 3i omega plus 2. If we have c equal to minus k by m, comma, minus d by m and d equal to 1, we compute h sigma of omega equal to minus omega square divided by minus omega square plus 3i omega plus 2. Figure the displacement top left, velocity top right, and acceleration bottom. Frequency response for the mass spring damper system when d equal to 3 and k equal to 2. We take d equal to 2 and k equal to 1 with the c equal to 1, 0 and d equal to 0, 1. We compute h sigma of omega equal to 1 divided by minus omega square plus 2i omega plus 1. The corresponding board plot is the first plot in below figure. Next, with c equal to 0, 1 and d equal to 0, 1, we compute h sigma of omega equal to I omega divided by minus omega square plus 2I omega plus 1. And the corresponding board plot is the second plot in below figure. If we have c equal to minus k by m, comma, minus d by m and d equal to 1, we compute h sigma of omega equal to minus omega square divided by minus omega square plus 2I omega plus 1. The board plot for this frequency response function is the third plot in below figure. Figure the displacement top, velocity top right and acceleration bottom frequency response for the mass spring damper system when d equal to 2 and k equal to 1. We take d equal to 2 and k equal to 10. With c equal to 1, 0 and d equal to 0, 1, we compute h sigma of omega equal to 1 divided by minus omega square plus 2I omega plus 10. The corresponding board plot is the first plot in below figure. Next, with c equal to 0, 1 and d equal to 0, 1, we compute h sigma of omega equal to I omega divided by minus omega square plus 2I omega plus 10. And the corresponding board plot is the second plot in below figure. If we have c equal to minus k by m, comma, minus d by m and d equal to 1, we compute h sigma of omega equal to minus omega square divided by minus omega square plus 2I omega plus 10. The board plot for this frequency response function is the third plot in below figure. Figure the displacement top left, velocity top right and acceleration bottom frequency response for the mass spring damper system when d equal to 2 and k equal to 10. We take d equal to 0 and k equal to 1. With c equal to 1, 0 and d equal to 0, 1, we compute h sigma of omega equal to 1 divided by minus omega square plus 1. The corresponding board plot is the first plot in below figure. Next, with c equal to 0, 1 and d equal to 0, 1, we compute h sigma of omega equal to I omega divided by minus omega square plus 1. And the corresponding board plot is the second plot in below figure. If we have c equal to minus k by m, comma, minus d by m and d equal to 1, we compute h sigma of omega equal to minus omega square divided by minus omega square plus 1. The board plot for this frequency response function is the third plot in below figure. Figure the displacement top left, velocity top right and acceleration bottom frequency response for the mass spring damper system when d equal to 0 and k equal to 1. A quick and dirty plotting method for board plot. It is possible with varying levels of difficulty to plot board plots by hand. The first thing we do is rearrange the frequency response in a particular way suitable to our purposes. The form desired is h of omega equal to k product j1 equal to 1 to k1 1 plus I omega tj1 into product j2 equal to 1 to k2 1 plus 2I zeta j2 omega divided by omega j2 minus omega divided by omega j2 the whole square divided by I omega whole power k3 product j4 equal to 1 to k4 1 plus I omega tj4 into product j5 equal to 1 to k5 1 plus 2I zeta j5 omega divided by omega j5 minus omega divided by omega j5 the whole square, where the t's, omegas and c's are real. The c's are further between minus 1 and plus 1 and the omegas are all positive. The frequency response for any stable minimum phase system can always be put in this form. For non-minimum phase systems or for unstable systems, the variations to what we describe here are straightforward. The form given reflects our transfer function having K1 real zeros at the points minus 1 divided by Tj1, comma J1 equal to 1, comma etc. K1. Number 2. K2 pairs of complex zeros at omega J2 into minus zeta J2 plus or minus square root of 1 minus zeta J2 square, comma J2 equal to 1, comma etc. K2. Number 3. K3 poles at the origin. Number 4. K4 real poles at the points minus 1 by Tj4, comma J4 equal to 1, etc. K4. And number 5. K5 pairs of complex poles at omega J5 into minus zeta J5 plus or minus square root of 1 minus zeta J5 square, comma J5 equal to 1, etc. K5. Example. We consider the transfer function T of s equal to s plus 1 by 10 the whole divided by s into s square plus 4s plus 8. To put this form in the desired form, we write s plus 1 by 10 equal to 1 by 10 into 1 plus 10s. Now the denominator is expanded as s square plus 4s plus 8 equal to 8 into 1 plus 1 by 2 into s plus 1 by 8 into s square. The term s is multiplied and divided by 2 root 8. Hence we get 8 into 1 plus 2 into 1 by 4 s divided by root 8 plus s by root 8 the whole square. In the next step, root 8 in the s term and 4 in the denominator get cancelled and we get an equation 8 into 1 plus 2 into 1 by root 2 into s by root 8 plus s by root 8 the whole square. Thus we have a real 0 at minus 1 by 10, comma a pole at 0, comma and a pair of complex poles at minus 2 plus or minus 2i. Thus we write, substitute the expanded values. T of s equal to 1 by 80 into 1 plus 10s divided by s into 1 plus 2 into 1 by root 2 into s by root 8 plus s by root 8 the whole square. And as h of omega equal to 1 by 80 into 1 plus I10 omega divided by I omega into 1 plus 2i into 1 by root 2 into omega by root 8 minus omega by root 8 the whole square. Board plot for each of the basic elements. H of omega equal to k. The board plot here is simple. It takes the magnitude 20 log k for all values of log omega. The phase is 0 degree for all log omega if k is positive and 180 degree otherwise. H of omega equal to 1 plus I omega t. For omega near 0, the frequency response looks like 1 and so as the value of ODP. For large omega, the frequency response looks like I omega t and so the log of the magnitude will look like log omega t. Thus the magnitude plot for large frequencies we have modulus of h of omega equal to 20 log omega TDP. These asymptotes meet when 20 log omega t equal to 0 or when omega equal to 1 by t. This point is called the break frequency. H of omega equal to 1 plus 2i zeta into omega by omega naught minus omega by omega naught the whole square. For small omega, the magnitude is 1 or 0 dp. For large omega, the frequency response looks like and so the magnitude looks like the phase starts out at 0 degree and goes to 180 degree as omega increases. H of omega equal to I omega the whole power minus 1. We can also read the whole inverse. The magnitude is 1 by omega over the entire frequency range which gives modulus of h of omega equal to minus 20 log omega dB. The phase is minus 90 degree over the entire frequency range and the simple board plot h of omega equal to 1 plus I omega t whole power minus 1. The analysis here is just like that for a real 0 except for sines. The board plot is shown in for t equal to 1. H of omega equal to 1 plus 2i zeta omega by omega naught minus omega by omega naught the whole square whole power minus 1. The situation here is very much like that for a complex zero with sign reversal. Figure both plots for h of omega equal to 1 plus I omega left and for h of omega equal to 1 plus 2i zeta omega minus omega square for zeta equal to 0.2, 0.4, 0.6, 0.8 right. Figure both plots for h of omega equal to I omega the whole inverse left and for h of omega equal to 1 plus I omega the whole inverse right. Figure both plots for h of omega equal to 1 plus 2i zeta omega minus omega square whole power minus 1 for zeta equal to 0.2, 0.4, 0.6, 0.8. The polar frequency response plot. The idea here is that rather than plotting magnitude and phase as one does in a board plot, one plots the real and imaginary part of the frequency response as a curve in the complex plane parameterized by omega belongs to 0, infinity. Doing this yields the polar plot for the frequency response. One cloud do this, for example, by taking the board plot and for each point omega on the independent variable axis, put a point at a distance modulus of h of omega from the origin in the direction. Indeed, given the board plot, one can typically make a pretty good approximation of the polar plot by noting the maxima and minima of the magnitude response and the phase at these maxima and minima, and the magnitude when the phase is 0, plus or minus 90 underscore, or plus or minus 180 underscore. Figure polar plots for h of omega equal to 1 plus I omega top left, h of omega equal to 1 plus 2i zeta omega minus omega square, zeta equal to 0.2, 0.4, 0.6, 0.8 top right, h of omega equal to 1 plus I omega the whole inverse bottom left, and h of omega equal to 1 plus 2i zeta omega minus omega square the whole inverse, zeta equal to 0.2, 0.4, 0.6, 0.8. Time domain analysis. Time domain analysis is a process of finding the response of a system y of n of t to a given excitation x of n of t. The graphical representation is also shown below, where the x of n of t and y of n of t are held in the y-axis and not in the x-axis. Three different methods are available for the time domain analysis of discrete time systems: induction method, state space method, Z transform method. Induction method. The induction method involves solving the difference equation using induction. This method is somewhat primitive and inefficient. However, it is an intuitive method that demonstrates the mode of operation of a discrete time system. It is useful as an introduction to time domain analysis, but it tends to become quite complicated in higher order discrete time systems. State space method. The state space method entails the manipulation of matrices. It is quite useful in applications where routines for the manipulation of matrices are available, example in MATLAB. It is applicable to time dependent systems. Z transform method. The Z transform method is the most efficient and most frequently used method among the available methods. Its main advantage is that it cannot be applied to time dependent or non-linear systems. Example: find the impulse response of the recursive system. Here x of nt is summed up with p, which has already been multiplied by y of nt, since the t is in the reverse direction in between the points a and b, assuming an initially relaxed system. Here x of nt is summed up with p, which has already been multiplied by y of nt, since the t is in the reverse direction. Solution. The difference equation is y of nt equal to x of nt and p into y of nt minus t. If x of nt equal to delta of nt, we have y of nt equal to delta of nt plus p into y of nt minus t. For an initially relaxed system, y of nt equal to 0 for n less than 0 and y of 0 equal to delta of 0 plus p into y of minus t equal to 1 plus 0 equal to 1. Y of t equal to delta of t plus p into y of 0 equal to 0 plus p into 1 equal to p. Y of 2t equal to delta of 2t plus p into y of t equal to 0 plus p into p equal to p square, etc. Y of nt equal to u of nt into p power n. The unit step u of nt is added to ensure that y of nt equal to 0 for n less than 0. Example, assuming that the system shown is initially relaxed, find the unit step response. Here x of nt is summed up with p, which is already been multiplied by y of nt, since the t is in the reverse direction in between the points b and a. Solution. The difference equation is y of nt equal to x of nt plus p into y of nt minus t. If x of nt equal to u of nt, we have y of nt equal to u of nt plus p into y of nt minus t. For an initially relaxed system, y of nt equal to 0 for n less than 0, and hence we have y of 0 equal to u of 0 plus p into y of minus t equal to 1 plus 0 equal to 1, y of t equal to u of t plus p into y of 0 equal to 1 plus p, y of 2t equal to u of 2t plus p into y of t equal to 1 plus p square, etc. Y of nt equal to u of nt into summation k equal to 0 to n power k. We can write y of nt equal to u of nt into 1 plus p square plus etc. p power n is called equation number A. P into y of nt equal to u of nt into p square plus etc. p power n plus p power n plus 1 is called equation number B. Subtracting equation A from equation B, we get y of nt minus p into y of nt equal to u of nt into 1 minus p power n plus 1, or y of nt equal to u of nt into 1 minus p power n plus 1 divided by 1 minus p. Therefore, there are three cases to consider: p less than 1, p equal to 1, p greater than 1. For p less than 1, the steady state response is obtained by evaluating y of nt for n tends to infinity, that is, limit n tends to infinity, y of nt equal to 1 divided by 1 minus p. For p equal to 1, y of nt equal to limit p tends to 1 d of 1 minus p power n plus 1 divided by dp divided by d of 1 minus p divided by dp equal to n plus 1. Hence, limit n tends to infinity, y of nt tends to infinity. For p greater than 1, limit n tends to infinity, y of nt is approximately equal to p power n divided by p minus 1 tends to infinity. Sinusoidal response. The time domain analysis has shown that response of a first order recursive system to a sinusoidal excitation of unity, amplitude and zero phase angle, that is, x of nt equal to sine of omega nt, is a sinusoidal of amplitude m of omega and angle theta of omega, that is x of nt equal to m of omega into sine of omega nt plus theta of omega, provided that the transient component decays to 0. It turns out that this general property of recursive as well as non-recursive systems in general, the transient response of a discrete time system will decay to 0 only if the system is stable. Conclusion. In this chapter, we have covered the following in detail: time domain analysis, frequency response graphical interpretation, application digital audio effects.